So when you do all of that, you have to choose horizontal grid spacings. Okay, you have to set up your model domain, you have to allocate water depth to it, and then you have a constraint for your choice of the time step delta t, and you have a stability condition, and it's called the CFL stability criterion, and this is how it looks like. You have to choose your time step, okay, according to this requirement. And it actually can be a very, very tough requirement because it depends on the horizontal grid spacing, but also on the total water depth. Okay, so if you want to do simulations in the considering deep ocean, then you might be constrained to very, very small. This one is often a very, very tough condition. So now another thing. So we tested this model already, okay, and we tested this model with a quadratic lake with a bathymetry, and I showed you how to produce a variable depth distribution like shown on this map. We forced this model with a southerly wind, all the same wind, okay, and we achieved a steady state simulation. Let's see whether that comes on the next slide. And you can produce and you can add floats, Lagrangian particles floats to the model, and you can simulate so-called trajectories, the history of the float. But now the next thing we want to do actually we want to simulate the advection of a Eulerian tracer, like a concentration field. And you can imagine that the concentration is everywhere zero, and somewhere you add a tracer, a patch of tracer where the concentration is 1, and then you want to, like an oil spill, if you like, and then you want to simulate where does this oil spill go. So this is all it is about here. Not the advection of particles, it's the advection of a concentration field. That's a totally different story.